Encoding, getting information in, storage, which is really going to be change structure of your brain activity, and then retrieval, which is always going to be related to the output system. Now, where we're going to be going from this point to the end of the chapter is simply to walk through those 3 steps. We're going to cover encoding, then we're going to cover storage, and then we're going to cover retrieval. And at the very end of the chapter, we'll cover a variety of applications or unique aspects like false memory, for example, to see how a false memory is actually formed from encoding, storage, and retrieval functioning together in one fluid component. Encoding. Encoding is defined as the process during which you receive input through one of your 6 sensory systems. Nothing more, nothing less. Encoding is all about sensory reception and, of course, how much overplay receptors generate at the receptors themselves to continue feeding information into your brain. Because the more information you feed in from any one receptor, the higher the likelihood that that pathway will wind up resulting in information being established or recognized in short-term memory. So pain, even though you may have only a small number of cells being activated, if you stabbed yourself with a pin or touched a hot surface with just one part of your finger, it's very likely that it will become something you'll be aware of, right? It'll get into the attention aspect, the center component, short-term memory, and rehearsal of your information processing model of memory. But things that are associations between things like irrelevant aspects of your environment or things that are not relevant at the current time simply will wind up being lost. Now, for the things that are encoded, they all follow the same general principles that we saw back in the learning chapter. In terms of psychophysics, for example, if you cannot detect change in stimuli, then any change in a stimulus will have no effect on you. So the roles of absolute and difference thresholds, and in fact, on a practical basis, primarily difference thresholds, serve as a primary point at which any environmental stimulus can influence you. So there has to be something that you detect. And of course, the least amount of change that you can detect is called a just noticeable difference, right? Terms from the sensation and perception chapter from the field of psychophysics that are very relevant here. Any stimulus that affects you must have met its just noticeable difference. And of course, the just noticeable difference is going to be dependent upon the location you are in terms of the stimulus intensity. Because the higher and higher the level of stimulus intensity, the greater and greater in the absolute change that is necessary before you can detect any difference. And that, right, remember, was a whole story of the issue of the Weber constant and Fechner's development of the just noticeable difference. Other factors that came from the sensation and perception chapter, Gestalt. Remember, Gestalt refers to a context. No stimulus ever affects you by itself. A stimulus is always modified by the context that it's in, and the context actually has a very substantial influence on modifying the stimulus itself, or the identified stimulus, and so you always have to pay attention to contextual cues. Attention, as we were talking about earlier, attention refers to that center section of the information processing model, and you have one attentional resource, which is a very important thing to keep in mind, because as you multitask, you always divide your attention across different things. You never subdivide your attention. That's not possible. You only use the one attentional resource and distribute it across the many things that you are paying attention to. All the aspects of sensory and perceptual illusions that we talked about back in the sensation and perception chapter are relevant in this case. All of the aspects of neuroplasticity and the scads of actual biochemical pathways that are related to the various forms of neuroplasticity are all relevant in this case. And what we're going to see now are the last two bullet points, the space, durations, and frequency of events, and symbolic meaning, which are components of encoding that we're going to start addressing at the current time. Now, there are two types of encoding, automatic processing and effortful processing. And automatic and effortful are going to be affected by the space, duration, and frequency versus symbolic meaning. And in fact, we'll see space, duration, and frequency be connected to automatic processing and symbolic meaning being connected to effortful processing. But in terms of encoding, the two processes that you're looking at here, automatic and effortful, automatic simply means it requires no effort. And in fact, the unique thing about automatic processing is that any event that you experience that fits within the parameters of automatic processing automatically becomes a long-term memory. And that's why it's called automatic in this case, because you are automatically establishing a long-term memory from it. In fact, it's a system that you can't even turn off. There are simply some things that you experience that you will automatically form long-term memories of, and you will not be able to stop yourself from being able to do so. This type of memory clearly exists in both animals and humans. Effortful processing, as we're going to see, requires a great deal of attention and conscious effort. And in fact, the system that is going to be engaged most forcefully in effortful processing is going to be the process of rehearsal. Repeating, repeating, repeating. Information that will be of a symbolic form, like language, will have to be repeated over and over and over again before it can be turned into a long-term memory. Now, automatic processing. For information that occurs without effort, there are going to be three primary stimulus dimensions that form an automatic long-term memory. And those are space around your body, the duration of an event, and the frequency of an event. Space, duration, and frequency. Okay, and so that is basically space and time. And when you mix space and time together, you'll have an event that occurs at a particular time, and then you can derive from that the number of times the event occurs, which is now frequency. So I have mentioned this, I believe, in a previous chapter, but the only thing that your nervous system really seems to have evolved as a capacity to do is to evaluate space and time. And everything that we know as human beings always involves aspects of three-dimensional space and time durations, and then just derived variations of those things, which may be oftentimes very complicated, but there's nothing more basic than the passage of time and specific physical locations with respect to yourself. If you're curious to see how long-term memories actually are formed through space, duration, frequency, I can ask a few simple questions of you. For example, I'll ask you something that you probably don't think is relevant at all, but you very likely know the answer to. Think about homeroom class when you were in 5th grade. Where did you sit? Okay, that's the question. Where did you sit in homeroom during 5th grade? Or I could probably even ask, do you remember the layout of the room when you were in kindergarten? And my guess is almost everybody will be able to say yes to both those both of those questions. And that's just the point. Space around your body automatically becomes a long-term memory. And so you just automatically remember all spatial aspects of events that you are exposed to. And when you're exposed to the same thing over and over and over again, so for example, for the 9 months that you may have been in kindergarten, you will remember how the room was laid out because that same spatial stimulus was something that was presented to you over the course of 9 months. And not only was it formed as a long-term memory, but it was formed as a long-term memory over the course of 9 months, over and over and over again. I mean, I can remember where, or how the room was laid out in the kindergarten class that I was in, and the portable building that I was in. In fact, the portable building that I went to kindergarten in actually still exists and is still used as a kindergarten. I can remember where we played because the entire setup is still the same. Other things like such as duration. The last time you were driving, think about the very last red light you experienced. Completely irrelevant issue. But when you got stopped at a red light the very last time that you were driving, do you think you can estimate accurately about how long you were actually there? And there's probably a reasonably good guess that you could probably make. And in fact, if you think about that same traffic light, if that's a common path that you drive through in your neighborhood, for example, how often do you get stopped at that traffic light, right? Is it all the time? Sometimes. Now, when we're in class together, I oftentimes use the traffic lights coming into campus. And if you come into campus off of Glades Road, how often do you get stopped at a red light on Glades Road before you can actually enter campus while you're driving? And most people can give an answer almost immediately. And in fact, one of the more common ways in which I do this to add in space, duration, and frequency is to ask if we were all together in class, if you got stopped at a red light today coming onto campus, which car were you in line? Were you the first car in line, the second car in line, the third car in line? If you were in a left-hand turn lane, were you in the left turn lane or the right left turn lane? How many cars were you from the front or the back? Most people actually have a reasonably good idea where they were, how long they actually sat there in their car, and how often they get stopped at a red light as well. In fact, when you start evaluating space, duration, and frequency in terms of any of your memories, you'll actually be surprised at just how much information you've retained about your life. In fact, one of the things that we're going to wind up seeing about this issue is that if we get back to your 5th grade class again, you might remember where you sat, but not the names necessarily of the people who literally sat right around you in 5th grade class. And the reason is the information for who sat around you is going to be language information. You know, Joe Schmo and Susie Smith and Mary Jones, and these are the people that sat around you. And because they have names, names are symbolic processing. What we're going to find is symbolic processing is actually an aspect of effortful processing, things that form long-term memories much more difficult, with much more effort needed. And as a result, you'll remember where you sat, but not the names of the people you sat around. So let's move on and take a look at this question. Which of the following is not automatically processed? All right, I'll give you a minute to look at that. And the correct answer, which one is not automatically processed? The answer would be D, the seat assignment shown on your concert tickets. Seat assignment shown on your concert tickets would tell you what section you're in, what row, and what seat. So the last time you went to go see Justin Bieber, you may have been in section Q, row L, seat 5. That's very unlikely information that you'll remember because section Q, row L, seat 5 are all aspects of symbolic processing, right? They are things we talked about back in the developmental chapter. They are symbols for other things. You know, the number 5 is just a symbol that refers to the 5th chair in a row. Letter L is a designator for a particular row in a particular section, which is section Q. All of these symbols identify where your chair is, but they're not the memory of the spatial dimensions around you. When you sat in section Q, row L, seat 5, you very well may remember where you sat and your view of the stage and who was around you in general and the kinds of events that occurred, all related to space, duration, and frequency. But the actual seat assignments, no. The other answers, like for A, the furniture arrangement in your apartment, that's definitely a spatial arrangement. So that's space. Likelihood that the phone will ring, that is a frequency issue. How long you spent in the shower, that is a duration issue. The people around you while shopping, again, space. The people around you, whether it was crowded or not crowded. In fact, I could ask you, the last time that you went shopping, was it crowded in the checkout line? And there's probably a very good chance you actually remember accurately. Whether it was or wasn't will be specific to you, but your ability to answer that question is going to be very likely true. So that moves us on to effortful processing. Now, effortful processing, as I was implying, always requires symbols. Anything that is processed with effort that requires very specifically the rehearsal component that is connected to short-term memory is always anything that is symbolically processed. And that leads us back to the whole story of symbolic manipulation in the pre-operational stage of the developmental chapter. Because the development of symbolic manipulation is one of the basic underlying principles that develops your ability to have better language skills, to develop mathematical skills, and to start to recognize that other people have thoughts different than yourself. All of that was, again, related to the pre-operational stage in the Piagetian stages of development from the developmental chapter. And you're seeing symbolic manipulation come back to you again, which is not a surprise because you're still dealing with the same brain, and so the same principles keep coming back to you, given that we're dealing with how behavior is managed. So email addresses, made up of letters and numbers, a dot, an @ sign, other types of symbols possibly, phone numbers, strings of numbers, those are all symbols, grocery lists, those are all words, words are symbols, concepts are just broader connections of words themselves. Names and dates are, of course, all symbols because a name refers to a person, a date refers to a particular time. Names and dates are not the people and the time periods themselves, they always refer back to the other thing. They are always symbolic in nature, as well as mathematical equations. Mathematical equations work essentially just like human language does. If you speak about English, French, or Spanish, there's a particular grammar, which is a structure in the way in which you take words and order them. And the order of the words establishes in part the meaning of what the sentence means. And the exact same thing happens with a mathematical equation. You cannot take all the plus, minus, and division symbols and put them together and then just have a string of numbers after that, right? That would be a corrupted mathematical equation. It would make no sense. You have to string things together in the proper mathematical grammar, which is the same thing you do with human language. You have to have your subject, verb, and object in the proper order for the particular language that you're dealing with, and that helps establish the meaning. So everything that you actually see in terms of effortful processing really is very consistently academic work, because what you do as a student is learn by using symbolic manipulation. That is, more specifically, you're using language. You learn everything through language in school. You learn names, dates, concepts, mathematical equations, everything, including even if you're learning to do painting, there will be a sequence of steps that you have to follow that you're going to be taught. If you're dancing, you're going to learn the particular, not just the dance steps themselves, which are motor behavior, but you're going to have to learn the sequences and the names for the movements and so forth, which is again all symbolic processing. Everything, that is everything you do in terms of academic work as a human being is always effortful processing. And effortful processing, just to beat you over the head with this information, always requires this: rehearsal. The rehearsal component from short-term memory, which comprises the larger aspect of attention in this entire center section of the information processing model. And why this is important is because you may be curious about whether or not there's a way to just kind of feed memories into your brain. We talked about whether or not you could listen to a book on tape when you go to sleep and wake up in the morning and have all the knowledge, already at your fingertips when you wake up in the morning. And that, of course, doesn't happen. But you did see a little bit of stuff, a little bit of something there, where you had associations being presented during REM sleep that enhanced memory. But you can't just straight up learn while you're asleep, because systems function differently. And the same thing is happening here. When you are going to be doing academic learning, so everything that you see here, any academic learning, is always going to be effortful processing. You always have to come back to the rehearsal section of short-term memory and engage the entire process of rehearsing information to maintain it in short-term memory, which will then place it as long-term memory. And long-term memory may be relatively weak if it's not a very well-established memory and not connected to other memories. So you retrieve it, bring it back into short-term memory, and rehearse it some more, and then reestablish the memory. And around you go. Retrieve the memory, think about it, restore it, reestablish it as a stronger memory, then pull it back out again, think about it again, restore it as a long-term memory again, and over and over and over again. And what that should sound like to you is basically what you've always heard about studying. You repeat things to yourself, then you store it as a memory, and then you think about it. You remind yourself of these things. And reminding yourself is the process of retrieval, the capturing of the memory, the use of it in short-term memory, the restoring of it in long-term memory, and then again retrieving it back again. If you keep using this system of activating a memory, keeping it in short-term memory, and then reforming it again as a stronger long-term memory, you will wind up with better information stored overall. And then the information, which is always symbolic in nature, will be more easily connected to other types of memories, will more easily able to be recalled, and better used for creative problem solving. So let's take a look at a question in this entire process. Which of the following does not involve effortful processing? I'll give you a second to pause the video if you want, and then we'll come back with the answer. And the correct answer here is your place in line. Your place in line should stand out to you as a memory that is formed through spatial relations. That is space, duration, frequency. This is automatic processing. So where you were in line will automatically be processed as a long-term memory. Think about the last time you went to, Publix. When you got in line to pay for your objects that you were buying, were you at the end of a long line, or was it a short line? Was the line only a couple of people? Was it a whole bunch of people? It's probably something that you can remember accurately. All of the other options here, a page of text from a novel, is all symbolic processing, because a page of text, just like the words you're looking at on a screen now, are all symbols. The president's speech, whether it was written down or just an auditory recording, an audio recording, is going to be symbols. Remembering your age, right? Your age is a number is a symbol. Body art, people write sentences on themselves. Those are other aspects of symbolic processing as well. Now, there are some other things that occur with respect to encoding, and those are the degree to which you will likely remember something. And the degree to which you remember is going to be affected to a great degree on whether or not it has a visual, acoustic, or semantic encoding component to it. So what you may notice here is that you have 6 sensory systems. However, psychologists tend to have a focus on language processing because that's going to be one of the most common ways in which human beings learn information. And visual processing and acoustic encoding are going to be aspects of language because you either are reading language, making it visual, or hearing someone speak. Those are the most common ways. So there's a tendency to focus on those. You could be talking about encoding for balance or smell or taste, but most of those things are not as prized or as highly regarded, and so you just typically don't hear about it. So be aware, there is a selective focus on language-oriented things here and a complete ignoring of your other senses. Semantic encoding is, of course, you don't have any semantic receptors. The semantic is a combination of activity in your brain that gives meaning through symbolic processing. It's a part of that symbolic processing system that we talked about before. And why this information is related to encoding is because we had, back in the Sensation of Perception chapter, talked about visual capture. Visual capture, as I told you back then, was a process by which vision dominates all of your other senses. And so, of your 6 senses operating, vision always tends to be the primary modifier of your experience of the remaining 5 senses. And that is an issue that does hold true. But there was one little bit of information there that I held back from you, and that is, if you are dealing specifically with language information, that is, things that have to be symbolically processed, then vision turns out to actually be the worst way in which encoding will occur. So if you're dealing with non-symbolic information, then vision tends to dominate. But if you're dealing with symbolic information, like reading words, for example, then visual encoding actually tends to be the worst way to remember things. So for example, if you're looking at the slide here, and I said, let's make this slide that you're looking at right now an art project. And so how do we make this an art project? Well, I'm going to say, well, go ahead, look at the screen. Ready? Okay, now I flipped off of the screen. Now what I want you to do, and I'm only saying this hypothetically, is reproduce that same slide now as an art project. Duplicate every word on that screen in the font that it was in. Redraw the picture that was on the slide, and just copy it as though you had photographic memory, which of course you don't, which is something we haven't talked about yet. But reproduce that entire page. You would have a very difficult time being able to do that. And that would actually represent just how poor visual encoding is when you're dealing with symbolic information. One of the things that would actually work out better is if you had to remember what I was saying about this particular slide. Having heard me speak about this slide and lecture about it, you'd be in a better position to remember what was said by remembering the auditory memory of what you had heard. But your best memory would be the semantic encoding, which was, what did this slide actually mean? So if I flipped off the slide, you could just say, well, that other slide you were talking about was all about encoding and how visual capture is not really the best way to expect a memory to be formed if you're dealing with language. And that basically is correct. That is the basic gist of this particular slide. But if we asked you to reproduce it, from a visual standpoint, you would do a terrifically horrible job of reproducing this slide as an art project. Now, there's one final topic here that we're going to hit before we're going to finish this topic here, and that is the issue of the serial position effect. The process of memory can become fairly complicated, and we can't hit all of the complexity of memory in a general psychology course, but to kind of give you an idea of some of the processes that occur in terms of memory that actually have a fairly substantial influence on your ability to remember things comes from two aspects of interference called proactive interference and retroactive interference. Interference is a general name given to something that blocks your ability to remember something. That should be pretty straightforward. But oddly, it turns out that there's two forms of interference, proactive and retroactive. Proactive is a process in which any learning that occurs now interferes with what is going to come next. So if I tell you something now and you're thinking about it, the next thing that I tell you will be less well processed if you're still thinking about that first item. And the reverse can actually occur as well in retroactive interference when you're talking about backwards in time. That the thing that you're learning now, if you're focused on it very intensely, could actually make it more difficult to remember the thing that had happened just beforehand. And both of those processes actually occur. In fact, to kind of understand what's called the serial position effect that you see on the bottom of the screen, let's think of your memory as only engaging proactive interference. Only. In that case, what would happen is you would find only a memory system in which the very first thing you were told would always be best well remembered, and each successive item that you were told would be less well remembered. So your ability to remember things in a row of information would always be best for the first item and worst for the last item. And that's proactive interference because each item interferes with the thing that comes next. So the the first item interferes with the second, but then the third item in the list is going to be interfered by the first two. The fourth item in the list is going to be interfered by the first three, and so forth, which will continue to degrade your ability to remember. If we played out the process in terms of retroactive interference, you would see only this right-hand side of this curve. So that for each item that was learned, the item that comes after it always degrades your ability to remember the item that came before it. So the first item in a list would be degraded by the second item in the list, and then the third item in the list and the second item in the list would both degrade the first item. And then the fourth item in the list and the third item in the list and the second item in the list would all degrade anything that came before it, and so on and so forth, so that your memory would always be least good for the first item of the list and always best for the very end of the list. Because both of those processes occur, if you put them together, what you wind up seeing is that in any random list of letters, numbers, symbols, objects, whatever it is, it doesn't matter what the source of stimulus is, as long as they are randomly related to each other and there's no particular order to them, you will always wind up finding that the beginning of the list and the end of the list are always best well remembered, and the beginning of the list is going to always be least well remembered. And that is a process called the serial position effect. So that for any list of random items, like grocery items that you have to buy at the supermarket, you will always be more likely to remember the beginning and the end of the list, and least likely to remember the items in the middle of the list. If you take the items, of course, and you string them into a story format, then in a story format, they will have a particular order, and then the serial position effect will disappear. So for example, if I gave you, for example, a list of grocery items that were needed to bake a cake, you would experience a serial position effect for whatever order the list was given to you. However, if you were told to bake a cake in a particular order by taking certain objects and, greasing a pan with butter and mixing flour with milk and eggs and mixing it and having a whole sequence of events that occurs with those same items, then the serial position effect would disappear, because in a sequence, each event that occurs in the sequence always identifies what you would do next. And as a result, it's easier to remember how these things fit together. And in fact, as you might imagine, this is a basic mnemonic technique. If you want to remember a whole series of random items that you might have to remember for a biology class, for example, it's always good to place them in some sort of memorial order, some type of structure, because the structure always identifies when you're at one place what would actually come next. So in this question, the very end of our slides here, which of the following scenarios would not include the serial position effect? I'll give you a second to answer that. Okay, of the five answers there, the one that does not include the serial position effect is going to be E, remembering the steps to fix your lawnmower. Because the process to fix your lawnmower will follow a particular sequence, and they will always wind up cueing you in what to do next. All of the other items in some way are going to be relatively random, like a bunch of grocery lists, people you randomly meet at a party, 10 random digits, your Z number, which is essentially going to be a randomly generated set of numbers, of which you have to learn to repeat over and over and over again, like your social security number, until you finally remember it. That involves a lot of rehearsal to establish that long-term memory, because they are just random digits. But remembering the steps to bake a cake, fix your lawnmower, walk from one part of campus to another part of campus, always involves a particular sequence that always cues in the next component and thereby eliminates this whole U-shaped function that you wind up seeing with the serial position effect. Okay, we're going to stop here, end this video, and we'll come back and work with storage next.